Hey, hello, Kim 103. I think I got this all working now, so we're going to go through and talk about organic structures. And we're also going to get into that second activity of the properties of organic molecules today. Okay, so today's or this week's stuff is primarily about um, drawing molecules and kind of understanding their structures. So the main instructional aid for you is this book chapter here that you've seen linked there, and this kind of goes through how to draw these different types of structures. This is taken from an organic chemistry textbook, so it's maybe a little bit beyond what we've done so far, what you've done so far. So I just want to give you an introduction of some things that'll help you out before you get into that. So first, when we draw these structures, or when we predict these structures, we can use some rules that aren't always true, but are true enough of the time that that we can use them. And we're going to call them common bonding patterns. And you may have seen some of this stuff before, maybe not. Carbon usually makes 4 bonds to other atoms or other, besides itself. So that can look like something like this, where the carbon atom is connected in these 4 ways. It can also make multiple connections. So it could have 2 bonds going to one atom and then 1 to each other one. Or it could even have 3 to 1 and then 1 to another, or 2 and 2 in some rare cases as well. So this is just saying, like, this is commonly how carbon atoms bond. So if you see a molecular formula like C4H8, you can say, all right, well, I've got 4 carbons, and here's how I'm going to connect them up. And we'll practice that in a second. Let's list some of the other ones that we're going to deal with. Hydrogen can only make 1. So when we see hydrogen, we can only connect it to one other atom. Oxygen, 2. And the first 2 are pretty well fixed other than some unusual situations. But oxygen actually does have some different ways that it can bond. In what we're looking at, it's almost always going to be 2 bonds and then 2 of these electron pairs, which you'll see in the document there. So that just means it's going to connect to 2 other atoms. And then it can also do that through a double bond to one other atom. So that still counts as 2 connections there. If you see oxygen just connecting to one thing or just connecting 3, don't freak out too much. That does happen, but this will be the majority of what we see. And then finally, nitrogen. We're going to see connecting 3 ways. And again, that could be like this. It could also be 2 and 1, or it could be 3. And it has these little extra electrons on it as well. You don't have to worry too much about those extra electrons. You'll see them in the pictures, but if you don't draw them, that's okay. In your structures, if you don't draw them, that's okay, because we're not using them for anything else. All right, so keeping this in mind, now we can start putting together some molecular structures called Lewis structures. So to draw a Lewis structure, you take a chemical formula, which tells you how many of each atom is there, and you just put it together following the rules that we just talked about. And often there are multiple ways of doing that. So if we have a formula like C3H8, that tells us that this structure has 3 carbons and 8 hydrogens. Now, that sounds like there's a lot of different ways to combine that. But if we go back up and look at this, we can see that hydrogen only makes 1 bond, which means when we try to draw a structure of this, we have to put the hydrogens kind of on the outside, because we can't put them in the middle or they would have to connect to too many things. So that's not going to work. So let's draw our structure here by putting the carbons in the middle, connected to each other, and then the hydrogens around the outside. And then we can kind of check and make sure that everything looks good and works. So I want to make sure, I want to check two things. First, I want to check that I have enough atoms. I have the right number of atoms based on the formula. Then I want to check that I have the right number of connections based on these patterns up here. All right, so first check, do I have 3 hydrogens? Yes. Do I have 3 carbons? Yes. Do I have 8 hydrogens? Also yes. So that's good. Second check, do my carbons all have 4 bonds and my hydrogens all have 1 bond? Yes. So both checks, so that means this is a good, reasonable Lewis structure for C3H8. Now let's say, what if we went C3H6 instead? A different compound. So let's try to draw that. Again, we're going to start with our carbons. We're going to start putting the hydrogens around like this. And then as you'll see, we will run out of hydrogens. So 1, 2, 3, 4, 5, 6. That's my 6 hydrogens. But this carbon does not have 4 bonds. So that's a hint to us that we need to use one of these multiple bond type scenarios. Because with multiple bonds, you can have multiple connections with the same number of atoms. Now we have to be a little bit careful about how we do this. We can't just put one here, because now this carbon has 5 bonds instead of 4, and that's no good. Also, this one still has 3, so that's not going to work either. So what we can do instead is we can move one of these hydrogens over. So we'll move a hydrogen over to this side, and that kind of gives us room for that extra double bond there. And now when we go back and check, we have 4 bonds on this carbon, 4 on this carbon, and 4 on this carbon. So it works. We've got 3 carbons, 6 hydrogens. Each carbon has 4 bonds, and each hydrogen has 1. And that's how Lewis structures work. If we include other atoms and more atoms, we can start having a lot of different choices as to which structures. So in other words, there are multiple different structures that would fit that formula. So if we say C4H8O, let's give this one a try. We've got 4 carbons, 8 hydrogens, and an oxygen. Now I just kind of put those in order from left to right just to put everything down, but as we can see, this doesn't work. Why doesn't it work? Well, this carbon doesn't have enough bonds, and this oxygen doesn't have enough bonds either. So a simple way to fix that is to just add a double bond between carbon and oxygen. So now the carbon has 4 and the oxygen has 2, and that works. But that's not the only way that we can make C4H80 in a structure. There are lots of other choices. So we could have put a double bond between carbons, for example. And we could have put the oxygen in the middle of the chain of carbons. So that also works. C4H8O. 4 bonds on every carbon, 2 bonds on the oxygen. You can imagine the oxygen, we could have moved it in between these two. We could have put it off a double bond, but coming off over here. So there are lots and lots of different ways to do it. There's even ones that aren't in a chain, like this one. We could connect everything around in a like pentagon shape with hydrogens coming off the carbons. And that is also C4H8O. And we've got 4 bonds around each carbon and 2 bonds around the oxygen, 1 bond around each hydrogen. So that works as well. There's many, many choices. And the point of doing this, besides just practicing building these structures using those bonding patterns, is that a molecular formula, a counting of how many atoms are in the structure, is not really enough information when we have multiple different possibilities. So just give me a second. I have to check something, and I will be right back. Okay, we're back. Um, so when we talk about these types of structures, organic structures, when we say organic, we mean based on carbon. We need different ways of describing the structure besides just a molecular formula. And there's really three ways that we're going to represent structures. There's the Lewis structures that we just talked about. There's ways of making those structures a little easier, a little more quickly. Condensed structures, I'm going to call these both the same basic thing, condensed and partially condensed structures. And then the third way is not really the molecular formula. We're going to look at this thing called a line structure or bond line structure. And in the interest of time, I'm going to link to a different video explaining these from last year rather than go through it all again. It's the same information. But please let me know if you have questions or if you want me to talk more about one of these things. I am going to show you some examples, though, in these structures here. So let's take these three structures that we drew and convert them into these other formats. So these are Lewis structures. Condensed structures are where we take all the hydrogens and we kind of push them down or condense them onto the atoms that they are connected to. And the reason for that is that as these structures get bigger, there's lots and lots of hydrogens floating around everywhere. And it can be helpful to look at them more in like a group. So we can say this is a C with 3 H's. This is a C with 2 H's. This is a C with 2 H's. This is a C with 1 H and an oxygen. So to condense that down, we might take that top structure there and we might draw it as CH3, CH2, CH2, CH, and then have that double bond to the oxygen. And it could go either direction, whatever, something like that. And then sometimes we could condense this even further, particularly if we're like typing and we want to keep this all on one line. We can get rid of those lines entirely. And the way we would write this is CHO. And the reason for CHO is because since we know that hydrogen can only have one bond, we know that this can't be CHO because that hydrogen has too many bonds. So it has to be CHO. And that brings the next point of brings us to the next point of this, which is that these types of structures require some knowledge. So you couldn't really decode this structure necessarily unless you knew about these bonding patterns. Because you might think it just means, well, we'll put the H's in between the carbons, even though that's incorrect. So the more we condense and simplify and shorten the structure, the more knowledge you need to kind of decode it. Whereas a Lewis structure is something that anybody can look at and kind of know all the information from that. All right. So let's look at some of this other one, this condensed structure for this next one also. So if we draw a condensed structure over here, that might look like CH2, CHO, CH2, CH3. So I could leave the double bond in there. I could also leave it stretched out with all the bonds in there. And really, I could also condense this down and get rid of that double bond, but then I'm assuming that whoever's looking at the structure understands that it has to be a double bond so that the carbons get enough bonds. So often we leave those in there if it's not too hard to do, just to help people out. Now this last one kind of shows the some of the limitations of condensed structures, because when we have this ring, there's not really a great way to draw a ring and make it all into one line. So instead, we would probably keep those lines and do something like CH2, 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 and then put the O in there. So it's a little bit condensed there, but there's not a great way to actually make that all on one line. So, oh well. So then the next step from there is to go to these line structures or bond line structures. And this is especially useful as the structures get bigger and bigger. If we're going to draw amoxicillin in a Lewis structure, this is an antibiotic medication. It's a big structure. You got a lot of stuff to draw there, a lot of atoms, a lot of C's, H's, whatever. Also, when you have that many atoms, it can obscure some of the more important parts of the structure, like what do these actual shapes look like? How are things connected? How are they similar to other structures? So we can simplify this down and make it look like this. And we've lost some information here. So there's some things we have to know about how to do this. But we also gained a better description of the structure by doing that. So before we look at something this big, let's build those up from our smaller structures. And the way that these work, you can go through this document does a nice job of explaining all this. But you get these like zigzag lines. And the way they work is that anywhere two lines intersect or there's an end of a line is a carbon atom. So there's 1, 2, 3, 4, 5, 6 carbon atoms in this structure. And then from there, we can also figure out how many hydrogen atoms there are and where they are based on the rules, the bonding patterns that we've talked about. So we know, for example, that carbon has to make 4 bonds. So if we look at carbon 1 over here, we can see it only has 1 bond over to carbon 2. And that means there must be 4 or 3 other things bonded here that are not shown. And those 3 other things are hydrogen atoms. So we look at number 2 here. We can see that it makes 2 connections to other atoms. And because we need to get up to 4, that means there must be 2 other ones that are not shown. So also hydrogen atoms, and so on. So if we were to expand this into a Lewis structure, we would have 6 carbon atoms in a row. And we would have hydrogen atoms around the outside. So the overall molecular formula here would be C6H14. Yeah. We can also have branching carbons. So here there's a carbon up there. So 1, 2, this is also 6 carbons, but 1, 2, 3, 4, 5, and then the 6th one up here. We can branch them this way as well. And anything that's not carbon doesn't get cut like this. So if we are abbreviated. So for example, if you have an oxygen in there, that stays just as it would be. If it's an oxygen connected to a hydrogen, that's all still written there. So we don't take hydrogens off anything else except carbon. So let's go back to our notes here, and let's see if we can now convert these structures into those line structures. So we'll take this first one here, 4 carbons. 1, 2, 3, 4. Let's number them just to keep track. And then we have to put that double bond to oxygen coming off of the 4th carbon. Now that could go up, that could go down, whatever. But we do want to maintain these types of angles throughout so that it's clean to look at. We don't want things kind of like cutting through the middle here, if we can avoid it. For our next one here, CH2 double bond CHO CH2 CH3. We can do that also. So we can go CH2. There's our double bond. Then we go down to the O. Then CH2 and CH3. And it always helps to number your atoms. You can either number all the atoms or just the carbons, so that you make sure to account for everything. Because as you're doing your zigzagging, it's easy to accidentally put in an extra zig or an extra zag, and suddenly now you have too many atoms. So watch that. The shapes like this are relatively easy with the line structures. We have to make a 5 pointed ring, which would be a pentagon, and then the oxygen would be taking up one of those spots. So we might draw this like that. And that's line structures. So for the assignment, you need to go through and draw line structures from all of these condensed structures. Well, the first 3 are Lewis structures. The rest of them are condensed structures. So when you do this, you want to first expand this out into some sort of a condensed structure where you can see the connections, and then go to the line structure. So let's take, for example, this one, Q. Okay, like that. So we have to figure out what this is, how this is connected first. And we have to use all of our rules, bonding patterns and things like that we know to make sure that we're doing it right. So let's start with this beginning. What does this even mean? CH3 taken 3 times. Well, we have to think about this logically. Does that mean CH3, CH3, CH3 connected like that? It does not. And the reason for that is that these 2 carbons, here and here, have too many bonds. They have 3 hydrogens plus 2 more connections. That's 5 bonds. That's not okay. So too many connections there. That's not going to work. So that can't be right. So the only way to get this to work, so that each carbon has 4 bonds, is to actually make 3 separate CH3s that all then connect to that next C. Like that. Because then we've got this bare C here, which tells us that it has to be connected to 4 other carbons because there's no H's or anything else written there. So that C, in order to have 4 bonds, is connected to the 3 CH3 carbons, and then it's connected to the CH2, CH2, and the OH. So now we've got this, and this should help us to come up with a line structure, because we can kind of start visualizing what that line might look like. We've got 1, 2, 3, 4 carbons and the OH, so that's going to be kind of our main zigzag, and then we'll have these other CH3s coming off of it. So 1, 2, 3, 4, and then OH. And then I've got, we'll call these like 5 and 6, coming off of number 2. So they're also connected to number 2. So we can put those up there like that. All right, and now we've got a nice line structure for that. So go back on my channel, check out the rest, the last time I did this. You can see some more examples here. If you want me to give you some more, I can do that as well. And then you can try all of these, and that's your assignment for this part of the work. All right, moving on, unless there are any questions at the moment. So let's take a look here. This is the other part of the assignment. So now that you know some things about the structures, we can start looking at their properties. And this is another one of those activities where it starts relatively simply and then kind of builds up from there. But again, I want to help you out with some introduction before you get started on it. In these tables, you have organic compounds that are grouped together by something called functional group. And the functional group is listed over here. That's the name of it. So there's alkanes, alcohols, ethers, and amines. And you can see some structural similarities in those groups. So you can see like you've got, these are all just carbon and hydrogen. These have OH. These have an O in the middle. And then these have NH2 on the end. So they're grouped by these extra pieces that are connected to the carbons. And then you have some properties. So you have molar mass, which is a measure of how large the molecule is, kind of like the atomic weight. You have something called a dipole moment, which we'll get into in a second. You have boiling point, what temperature does it boil at, and you have water solubility, grams per 100 milliliters H2O, which means if you have 100 milliliters of water, how many grams of each of these substances could you dissolve? So the higher that number is, the better it dissolves in water. All right, this column here, dipole moment, there's actually an explanation there. Down here, the dipole moment is a measure of the polarity of the molecule. So this introduces this concept of, is a molecule polar or non-polar, which has to do with separation of charge. So does the molecule have a more positive side and a more negative side, or is it pretty much even throughout? If it's pretty much even all around, it's called non-polar. If it's got more of a positive and negative separation, it's called polar. Polar compounds tend to have stronger connections to each other, and they also tend to dissolve in water better because water is also polar. So when in the first question here says, considering the dipole moments of the molecules in table 1, which functional group is most non-polar? So if that column dipole moment is a measure of polarity, which is the most non-polar? Well, that's going to be the one with the lowest polarity. And so we can see that that is the first table, which is alkanes. All right, so some definitions were required there, but ultimately it's a fairly simple question. Which of these groups overall has the lowest numbers? All right, so then it says, in general, do polar compounds have higher or lower boiling points than non-polar compounds? Well, we can again look at the table here. And we can say, well, if I'm looking at comparably sized molecules, the ones in the alkanes compared to the ones in the, I mean, definitely these are higher, right? So I've got a 46 versus a 44 versus a 46, and I got 78, minus 23, and minus 42. So much, much higher boiling points here, somewhat higher here, lowest here, and that does seem to correlate directly with the dipole moment. So the lowest polarity, lowest boiling point, highest polarity, highest boiling point. So it's asking you to make these connections between looking at things on the table. Again, other than the things that we just talked about, you shouldn't need a whole lot of outside information here. You don't need to look up the answers to these questions. You should be able to find them just from the numbers and the data on the table. And then if you have questions or if some of these are not clear what you're supposed to do, certainly let me know. Remember that you have to read pretty carefully. There's a lot of detail in some of the sentences, some of the information. So for example, sorry, this thing's moving slowly at the moment. So for example, this one, number 2, often gives people some problems. A hydrogen bond, what is it? Well, in order to figure that out, you need to have read carefully the description of hydrogen bonding right here and understand what that means. And that's kind of your answer to that question. So if you're not sure how to answer some of them, go back, read more carefully, ask in the Discord so everybody can see your question. Maybe other people can respond to it as well. And then really the kind of the goal of this whole activity is this question number 5. Once you have gone through and learned the stuff from the packet, you should be able to look at some of these structures and decide which ones have high boiling points or low boiling points, which corresponds to high or low or strong or weak intermolecular forces. And you should be able to do that just looking at the structures. So I guess probably next week then, when we come back and look at this more, we will go back through and check some of these answers. So give it your best shot this week, and hopefully this makes sense and this is something you can do. As usual, let me know if you have any questions. Hopefully you can work through this stuff okay. We can also spend a little time in lab if we need to, going through this in person. That's always a good place to bring questions and ask questions just because we're there, and there's usually some downtime where we're waiting for something to happen, or if the experiment ends early, where we can go through some of this stuff. So if you're having some trouble here, bring your questions and we'll get it sorted out. Otherwise, hope everything else is going well, and have a good weekend. Bye.